All right, welcome to our quantum series. We're going right back to the beginning, to the very first major crack in the foundations of classical physics. And it all started with something you see every day, the simple glow from a hot object. So, how on earth could a simple glow threaten to upend everything we thought we knew about the universe? Well, because that glow, which scientists had measured with unbelievable accuracy, just refused to follow the rules. It broke every law they had, and that's a crisis you just can't ignore. So let's set the scene. It's the late 19th century, and physicists are obsessed with figuring out the light given off by hot things, like a glowing piece of metal. And the experimentalists in Germany, wow, they were getting incredibly good at measuring this stuff with pinpoint precision. Now, to keep things simple, they came up with an idea called a black body. It's not a real thing, it's more of a perfect ideal. Imagine an object that's a perfect sponge for all light and energy. It absorbs everything. And because of that, it's also a perfect emitter. When you heat it up, the light it spits out is pure, depending only on its temperature, nothing else. This made it the perfect test for their theories. And this is what their measurements looked like. The key thing to see here is the shape of these curves. No matter the temperature, the pattern is the same. The brightness of the light goes up, it hits a peak at a very specific color, and then it drops off again. This data was solid. You could repeat it 1,000 times. But nobody had a clue why it looked like this. So naturally, the theorists got right on it. They took out the big guns, all the trusted laws of thermodynamics and electromagnetism, really the core of classical physics, and tried to cook up a formula that would match this curve. And what they got? Well, it was an absolute catastrophe. See, the whole idea of classical physics was built on the assumption that energy is continuous. It's smooth, like water flowing from a faucet. You can have any amount you want, big or small. They figured the tiny vibrating bits inside the black body could give or take any amount of energy at all. But that's not what the data said. The data clearly showed a peak, and then it nosedived to zero, especially for the high-energy, short-wavelength light. And this right here just says it all. The best theory they had, called the Rayleigh-Jeans law, it actually worked okay for the long wavelengths over on the right. But look what happens on the left, in the ultraviolet part of the spectrum. The theory predicts that the energy should just skyrocket, on, all the way to infinity. This spectacular failure got a suitably dramatic name, the ultraviolet catastrophe. And let's be clear, this wasn't some tiny miscalculation. It was a prediction of infinite energy coming from a warm object. That's not just wrong, it's completely absurd. It was a giant blinking sign that the very foundations of physics were broken. So who's going to solve this mess? Enter our guy, Max Planck. By 1900, he'd been wrestling with this problem for years, and he finally found a solution. But it wasn't a triumphant eureka moment. It was what he later called an act of desperation, a crazy idea that he himself didn't really like. Planck basically took that core idea of smooth, continuous energy and threw it out the window. He said, what if energy isn't a smooth ramp where you can stop anywhere? What if it's a staircase? You can stand on the first step, or the second, or the third, but you can never, ever be in between steps. Energy, he proposed, comes in distinct, separate chunks. He called these little energy packets quanta, and he came up with a simple, powerful rule. The energy of one of these packets, E, is tied directly to its frequency, nu. And the thing connecting them was a totally new number, a fundamental constant of nature, which we now call Planck's constant, or just h. That's it. E equals h times nu. And when Planck took this wild idea that energy comes in steps and put it into his math, something amazing happened. It worked. It worked perfectly. His formula traced the experimental data exactly, completely solving the ultraviolet catastrophe. He had the right answer. The problem was, he wasn't sure he believed the reason why. This is one of my favorite parts of this whole story. You'd think the man who just launched the quantum revolution would be doing a victory lap. But no. Planck was a conservative physicist, and he was deeply, deeply uncomfortable with the implications of what he'd just done. I mean, listen to his own words from years later. He basically said it was just a mathematical trick, a purely formal assumption he made because he was desperate and just had to find a formula that worked. He didn't actually think energy was really divided up into packets in the real world. In fact, he spent the next few years trying to get rid of his own idea. He tried to merge it back into the safe, comfortable world of classical physics. But as he put it, that pesky new constant h showed itself to be obdurate. It was stubborn. It just wouldn't go away. And thank goodness it was stubborn. because what Planck had reluctantly invented as a mathematical fix was about to be proven, again and again, to be a fundamental truth about how our universe actually works. Since then, Planck's law has been confirmed everywhere we look. That faint glow left over from the Big Bang, the cosmic microwave background, it's a near-perfect blackbody curve. We use this principle to figure out the temperature of stars light years away. It's been tested in labs at every temperature you can imagine. It is absolutely undeniably correct. So even though Planck was just trying to fix one annoying little problem, he had, completely by accident, kicked open the door to an entirely new reality. His idea of the quantum wasn't the end of the story, it was the starting gun. Just 5 years later, a young patent clerk named Albert Einstein takes Planck's idea and runs with it, saying that light itself is made of these quanta. A few years after that, Niels Bohr uses it to finally explain why atoms don't collapse. The dominoes just started to fall fast. In the end, Planck gave physics the key to a whole new universe, but he was afraid to actually turn it in the lock. He opened a door he was scared to walk through. And the question that would drive physics for the next 30 years, and the topic of our next explainer, is simple. What was on the other side?